All right, so in the last video, we evaluated some limits of algebraic functions or algebraic expressions using the several different limit properties that we talked about at the beginning of this section. And even though we got valid answers, we also kind of made note of the fact that it takes a lot of work to use all of those properties one by one. So it turns out there's a much faster way of dealing with limits in certain cases. So before we talk about this, I want to go back to either of these really, but let's just look at this first one, this first problem. The limit as x approaches -2 of 3x squared minus x plus 5. So it turns out that if I just took that -2 right there and plugged it directly in for the x's, I would have gotten my limit. And you can verify that. -2, if you plug it into this x and you square it, that's 4 times 3, that's 12. 12 minus -2 is 14, plus 5, that's 19. So this limit I was able to evaluate literally just by plugging -2 into the function. In fact, the same thing actually would have worked for part B here also. So why did we go through all of these steps then, if we could have just plugged a number in? Well, it turns out that being able to just plug that number in to evaluate a limit doesn't always work. It works under certain conditions. We're not going to talk about the full extent of those conditions until the end of this chapter, but we will talk about certain classes of functions where you can do this. And that way of evaluating a limit where you plug a number directly in, we call that the direct substitution property. So here we have stated the direct substitution property. It says if P and Q are polynomials, and if C is any real number, then the limit as x approaches C of P of x is equal to P of C, and the limit as x approaches C of P over x, P of x over Q of x equals P of C over Q of C, as long as Q of C is non-zero. Now, if you're getting a little caught up in the notation here, remember, P of C is just what you get by plugging C into your polynomial, which is what we're saying, right? So basically, whether we're dealing with polynomials or rational functions, which is what a polynomial over a polynomial is, as long as plugging C into the denominator doesn't give me a 0, I can just plug C directly into either of those types of functions and I immediately get my limit without having to go through all of those limit properties. Now, like I alluded to before, there are more functions than just these two types, polynomials and rational functions, where we can use the direct substitution property. But for now, we're only going to be worrying about these two types. So moving on from here. So let's take a look at this next example. This blurb right here is what we kind of just talked about. I'd like to evaluate these limits here using the direct substitution property. So starting with this one, the limit as x approaches 4 of this cubic polynomial x cubed minus 4x squared plus 3x minus 11. Now, I could go through all of those properties that we did for the previous example and correctly find a limit, but the direct substitution property says that since this is a polynomial, I can evaluate this limit just by plugging this 4 directly in for these x's here. So that limit is going to equal 4 cubed minus 4x squared, I can write this way, 4 squared plus 3 times 4 minus 11. Okay, and now it's just arithmetic. You could go right into a calculator, but I want to point out something that might help you as kind of a shortcut. Here I have 4 cubed, and here I have 4 squared, but then times another 4. So altogether, this is also 4 cubed. What I have here is 4 cubed minus 4 cubed. Even if you don't know what 4 cubed is, it won't matter because these will subtract and give you a 0. Then I have 3 times 4, which is 12, minus 11, that's 1. So notice how much faster that is. We can evaluate that limit just by plugging it in. Next problem, part B. The limit as x approaches 6 of this rational function, x squared minus 1, over 4x plus 9. That's a rational function because it's a polynomial over another polynomial. If I were to plug 6 directly into my numerator and denominator, I would get 6 squared minus 1 over 4 times 6 plus 9. Now remember that substitution property, that direct substitution property, if we are looking at a rational function like this, we do need to make sure that our denominator is not going to be 0, but I can already see that it won't. So that means that we're not going to run into any trouble there. 6 squared is 36 minus 1, that's 35. 4 times 6 is 24, plus 9 would be 33. And that's simplified. I'm going to leave that just as that fraction, 35 over 33. Okay? Mentioning this as kind of a side note. In calculus, generally speaking, we try not to deal with decimals too much. Now, because this is a business calculus class and we deal with money and finance and stuff like that, there are a lot of application problems where we do want to deal with decimals because we'll round to like the nearest cent or something like that. But in a more general sense, in calculus, we tend to avoid rounding decimals as much as possible. Because as soon as you round something, you now have an approximate solution instead of an exact solution. So if I have a fraction, I tend to want to leave it in the form of a fraction. I'm not going to do 35 divided by 33 and write some decimal that I have to round. Again, unless we're talking about a situation where it's an application problem and it's more beneficial to have that decimal, we tend to avoid them, okay? Let's go on to this next example. I have 4 limits that I want to evaluate here. And in this case, we're looking at a piecewise function. So f of x is defined to be x minus 1 over x plus 5 when x is less than or equal to 3. Okay? And then it's x squared minus 2x plus 1 when x is greater than 3. So notice, even though it's a piecewise function, the two pieces are either rational expressions or rational functions or polynomials. And that means that I can still use that direct substitution property. The only thing I have to be careful about is if I'm taking the limit as x approaches 3, which if you notice the very last one is that type of a limit. So let's deal with a first. I want to find the limit as x approaches 1 of f of x. Okay, so I come over to my piecewise function and I see which of these two functions would I use when x is near 1. So if x is less than or equal to 3, I'm supposed to use this function. 1 is less than 3, so that means I'm going to be using this, this function, x minus 1 over x plus 5 for this limit. Now, I could go through some limit laws, or I could use a numerical approach, or any of the other things we've talked about so far. But because when x is approaching 1, we only care about this function right here, then we're really just dealing with a rational function. And rational functions are one of the types that we get to use the direct substitution property. So I get to just find f of 1 directly and see what that gives me. So f of 1 would be 1 minus 1 over 1 plus 5. 1 minus 1 is 0, and the denominator, as long as it's anything other than 0, 0 over that number is still going to be 0, so we do get 0 as a solution for that one, okay? The next 3 limits all concern x approaching 3, and you can probably see why I chose that, because 3 is the number where our function changes from one to another. So funky things can happen in piecewise functions at these like boundary numbers, if we want to call them that. So first, I'm looking at a one-sided limit. The limit is x approaches 3 from the from the left. That's what that minus sign represents. So remember, what this means is that we are approaching 3, but only using numbers that are smaller than 3 to do that. And here, remember, x is less than or equal to 3. That would be the time when I'm using this rational function. So for an approach from the left, I would be using that rational function still. And again, because we are still dealing with a rational function, I can evaluate this limit simply by plugging 3 directly into the function itself. 3 minus 1 over 3 plus 5. Okay? This is equal to 2 over 8, or 1/4, after simplifying. Okay? Now let's try a similar limit, but this time I want to approach from the right. So if x is approaching 3 from the right, then we're only using values of x that are larger than 3 to approach 3. And in my piecewise function, when x is larger than 3, I use this quadratic polynomial, not the rational function. So this time it's the same idea. Being a polynomial, I'm allowed to use that direct substitution property. And I'm going to plug 3 directly in to see what I get. So I get 3 squared minus 2 times 3 plus 1. Okay, 3 squared is 9. 2 times 3 is 6, 9 minus 6 is 3, plus 1 is 4. Okay, finally, the limit as x approaches 3 of f of x. This time it's not from the left and it's not from the right. It's a two-sided limit. So I don't get to use the direct substitution property here because I'm approaching from both directions, I'm using different functions on each approach. So it's not clear which one I would be plugging 3 into specifically. But we know that two-sided limits can be thought of as the common value that we would get from doing both of the one-sided types of limits, assuming both of them give me the same number. In this case, we've already evaluated both the left and right-sided limits, and we got different numbers in each case, which means that this limit actually does not exist. I would say does not exist. And I'll put the reason here. Since the limit as x approaches 3 from the left of f of x is not equal to the limit as x approaches 3 from the right of f of x. So if you were ever asked to justify why does this limit not exist, you would want to write something like this. This is showing that that limit does not exist because these two things don't agree. Okay, let's take a look at another example. Now here we have a limit involving a radical function. Okay, and in this case, I'm not looking at the type of function that we have for, that we get to use our direct substitution property for, because I'm going to try to find that page again. If you recall, coming back here, this direct substitution property is only letting us use that substitution method for polynomials and rational functions, which is what these are. This one is a radical, which has a polynomial inside of it. So can I use direct substitution? Well, it turns out I can, but only because there's one additional step I would do in the beginning. I can use one of my limit properties that we talked about at the beginning to bring that limit inside that radical. We know that that's something that we get to do with radicals. This becomes the limit as x approaches 10. And remember, we want to put the radicand, the expression on the inside here, in parentheses, just to show that we are applying that limit to the whole thing and not just the first term. Okay, but now if I look at what's inside the radical, I'm taking the limit of a polynomial now. And once we're here, I can see, oh yeah, I can just do direct substitution since that's a polynomial. So here is where we get to just plug a 10 in. Okay, so that's 2 times 10 squared plus 5.6 times 10, okay? 10 squared is 100 times 2, that would be 200. 5.6 times 10, when you multiply by 10, it just bumps the decimal point over, so that becomes 56. So 200 plus 56 is just 256. This is actually something that has a nice square root. The square root of 256 is 16. Okay? So notice I did this initial step here where I brought that limit in. But even if I didn't bring that limit in and I just said, let's try substituting 10 in right away, I still would have gotten this. And this is kind of what I was talking about before, where this direct substitution property actually does apply to more functions than just polynomials and just rational functions. And part of the reason why is because we have those other limit properties that assist us in getting to a step where we can do that direct substitution. Okay? So that's nice. That makes those limits a lot easier. But if that's all that we had to do for limits, just plugging numbers in, then we wouldn't be spending as much time as we are on it. And so now what we want to do is look at a lot of those cases where it's not a simple matter of just plugging the number into the function. So let's suppose once again that we're looking at some like rational function. The limit as x approaches c of p of x over q of x. And let's look at a case where q of x, if I plug c directly into that, so that would be q of c. Let's look at a case where q of c actually does equal 0. Because remember that direct substitution property says we can only plug c into this as long as q of c is not 0. But what if it is? It turns out that even if q of c is 0, that limit can actually still exist, but we can't find it using direct substitution, at least not right away. We need to do some work on it first. So here's an example to kind of consider. Suppose I wanted to take the limit as x approaches 1 of x plus 5 times x minus 1 all over x minus 1. This is a rational function. If I tried using direct substitution right away, then as soon as I plug a 1 in for that x there and that x there, I end up with 0 over 0. Okay? Don't make the mistake of assuming 0 divided by 0 is 1 just because a number divided by itself is usually 1. You can't divide by 0. So that's undefined. It's completely undefined, which means direct substitution has failed us. Does that mean that the limit doesn't exist? No, it does not. In fact, the limit does exist in this case, but we find it a different way. So what I'm going to do is I'm going to take this expression, x plus 5 times x minus 1 all over x minus 1, and I'm going to cancel the x minus 1's out. And that's just dividing them out. If you notice what's left after doing that cancellation, I get x plus 5. And if x plus 5 is a polynomial, I get to use direct substitution for that. I can plug the 1 directly in and I get 6. Now, you have to pay a little bit more attention to what's really going on here. When you cancel something out like this, basically what you're saying is that x plus 5 times x minus 1 all over x minus 1 is actually the same function as x plus 5, just simplified. And that's almost true. If you plug any number in for x over here, you should get the exact same thing if you plug that number in for x over here, with one exception, plugging a 1 in. As we already saw, if you try to plug a 1 in over here, then I'm going to end up with a 0 divided by 0 type of error. But if I plug a 1 in over here, we don't get 0 divided by 0, we get 6. That's the only time these two functions will disagree with each other. Another way of thinking about this, if you think of the function x plus 5, so x plus 5 is y equals x plus 5 is a line. It's going to look something like this, okay? And it's going to keep going. That means this function also looks like a line, except there's one issue. This function is not defined at 1. That means that it's going to have a hole right there at 1. Okay? If you notice, even though this function disagrees with this function at only that one point, the limit as x approaches 1 should still be the same number. Because we've seen before, if you just have a hole in your graph, then that's not going to change what the limit is, because we're never actually plugging 1 directly into this. We're just getting really close to 1. So this is going to be our approach anytime we get something called an indeterminate form. That takes me to this definition right here. If the limit as x approaches c of f of x and the limit as x approaches c of g of x are both equal to 0, then the limit as x approaches c of f of x over g of x is what we call an indeterminate form. So coming back up here, if I took the limit as x approaches 1 of my numerator by itself and my denominator by itself, then in both cases I'm taking the limit of a polynomial, which means I could use direct substitution. But when I do that, when I plug a 1 directly into my numerator and directly into my denominator, I get 0 in both cases. That makes this limit what we call an indeterminate form. Indeterminate forms may have finite limits. They may exist even if you can't solve them the most direct way. So typically what we do is we try to simplify the expressions to see if it gives us something where direct substitution does work. Here's another example. The limit as x approaches 3 of x squared minus 9 over x minus 3. So in this case, it may not be immediately obvious how to simplify this. So we start, and this is a common first step in these problems, we start by factoring anything that can be factored. X squared minus 9 is a difference of squares. It factors to x minus 3, x plus 3. My denominator, x minus 3, it's linear. It can't be factored anymore. But I can now cancel the x minus 3's that are appearing here. This becomes the limit as x approaches 3 of just the x plus 3 that I had in the numerator. And at this point, that is a polynomial. I can just use direct substitution. Plugging the 3 directly in gives me 3 plus 3, or 6. Okay? So this is really what the bulk of this section is going to be spent doing. Yes, there's some problems where you could just plug this number into using direct substitution like right away. But for the most part, there's going to be some simplifying that takes place. This is going to be what we spend most of our time doing, simplifying first and then applying the limit. I'm going to end this video here, but we're going to do more examples of this in the next video.